just occurs here. In this question, we're in a forest filled with mice. Between 1 year and the next, there's a fall in the population by 2.7%. Scientists come along, add 30 mice each year, wonder what on earth is going on after that. Is we're going to get a stable population or whatever? The population, if they were going down 2.7% each year, is going to vanish eventually. But this release of 30 mice each year complicates matters. So the position is that if we have 1 year's population, UN, and then the next year's population, what's going on is we're subtracting 2.7% of that. In other words, what's left is 97.3%. So each year 97.3% of the population remains. However, there's this extra factor that's been introduced of adding 30 mice. So part A is asking us to establish a recurrence relation where we're to find the next year's population. We're multiplying the previous year's multiplication by a number and then adding another number. So we now know that we've defined 97.3%. That's 97.3 out of 100. That's 0.973. There is the multiplying factor. The multiplier is 0.973. So that means 1 year's population, 97.3% of it's left to get the next year's population, but with 30 mice added to that scenario. So in that case, we now know that A is 0.973 and B is equal to 30. Now in part B, it says explain why the estimated population of mice will stabilise in the long term. Now, it's all to do with this factor 0.973. If that factor is bigger than 1 or equal to 1, we'll not get a stable population. It's only if it's less than 1 or bigger than 0, or technically bigger than -1. If it lies between -1 and 1, if that factor lies between 1 and -1, then we will get a limit. The population will stabilise. Now that's because it's a linear recurrence relation. So we would say the recurrence relation is linear. There's no squared terms or anything like that. It's just a straightforward linear expression. Something times UN plus a number is AX plus B is a linear expression. So the recurrence relation is linear, and since the multiplier, we have to identify that, the multiplier 0.973 lies between -1 and 1, there is a limit. So we'll get a stable limit in the long run and the sequence of numbers that this recurrence relation produces. So let's let the limit, that stable number in the population, be L, for instance. Then there's two ways of finding. You may well know formula B over 1 minus A. Let's do it a different way. If we had actually reached the limit, so 1 year we're looking at a population of L and we're finding 97.3% of that and adding these 30 extra mice to that, and we notice since it is the limit we've reached, that we get exactly the same population. So we have an equation to solve. Let's take 0.973L away from both sides and we'd be left with 0.027. L, and that would be equal to 30. So L would be 30 over 0.027. That's what we get here. There B is 30. 1 minus 0.973 gives us the 0.027. So it's time for calculator, and you can see 30 divided by 0.027 gives us 1111.11 and so on. But they do ask us for accuracy of nearest 100. So long-term population will be, now it's nearer 1100s than it is to 1200s. So it'll be 1100 to the nearest 100. So linear recurrence relation with a multiplier lying between -1 and 1 ensures there'll be a limit, and if we assume the limit's L, solve this little equation, we end up with 1100 to the nearest 100 as the long-term population of mice in the forest. That's Mr. Corsi signing out. Hope you enjoyed the video.